Anthony, can you hear me and see the screen? You can unmute yourself for a second.
I can hear you, Professor.
Okay.
So there's like a delay in my computer.
Okay. Were you having trouble signing on? Because I only have one person signed in.
What's that?
Did you have problems signing in today?
No, I mean, it took a second, but I got in.
Okay.
Professor, I had a question about like job prospects for solid.
Yeah.
So I was talking to my advisor yesterday, and I was just wondering, like, obviously, like internships and things like that are canceled, but like, I'm by the time I graduate, I'll have a lot of experience with, to having taken like quantum mechanics and basically classes that aren't really required, but are really handy for jobs and maybe grad school. And I was just wondering, like, what is the only thing I can go into process engineering, or what are the options?
No. So what I'd recommend is if you want to broaden your horizons, in addition to 339 and 440, take some design courses, the VLSI design courses, like VLSI 1 and all. So that way you can work both in device and circuit design or in processing.
Is that what you did when you worked at TI?
Yeah.
So, I mean, I don't really have a lot of experience in like digital logic though, and the VLSI class sort of like requires that. Is that something that jobs would expect me to know a lot about, digital stuff?
Not necessarily. So if you work at Texas Instruments, for example, they've kind of moved away from microprocessor manufacturing, and they do a lot of analog, mixed signal, high power. So, there's wonderful courses on analog circuit design taught by Karpuri and Nansan. And that turns out to be a very nice growing niche area. And it requires a lot more knowledge about basic device physics. Okay, so it's not just ones and zeros. You really have to understand the devices to design those circuits.
Do you know what like most graduate students in solid state usually where they end up, like job wise, like what they end up doing?
Sure. And from my group and from MRC, it turns out for the last, maybe 10 years or so, I'd say 60 to 70% have ended up at Intel. I mean, they're this huge vacuum pump, right? And then a few have gone to IBM, Yorktown, TI, Micron. And then some of the Korean students have gone back to Samsung. So those are the big players. If you have some background in circuit design, then you have a lot more options because, for example, you have ARM in town. So I broaden my horizons and do not just device processing and device physics, but also a little bit of design. Okay.
Thank you.
I mean, overall, the job prospects in our field are actually quite good. They've always been.
Yeah.
Okay, let's get started. I'm going to quickly review what we discussed last time about MOS capacitance voltage behavior. Just to refresh your memory, we started looking at a MOSFET where you have the grounded source, drain voltage VD applied to the drain and a gate voltage VG. And we said that if you have a gate voltage in excess of what's called the threshold voltage, you induce an inversion layer of electrons, in this case on a p-type silicon substrate. And that inversion layer is shown by this lightly dotted blue region connecting the N plus doped source to the N plus doped drain. So it's kind of like a induced N-type resistor. Of course, you could flip all the polarities, and in a PMOS, everything would be changed. You'd have P plus source drains, N-type substrate, and so on and so forth, okay? The reason this N-type inversion region is formed in a MOSFET is when you apply a high enough gate voltage, you reduce potential barrier between the source and the channel. And if you have highly doped source and drains, carriers can simply spill over from the source drain regions into the channel region. On the other hand, if you just had a MOS capacitor without the N plus source drains, the only way you'd form these inversion layers would be by collecting minority carrier electrons that are present in the P-type silicon substrate. Those would have to diffuse through the depletion region and collect at the surface. Keep that in mind because I'll touch upon that in a second when I look at the CV characteristics, all right? So then we said that in the MOSFET, initially when you apply low drain bias, the field along the channel is small, so I'm going to be in the ohmic region, and the carriers will travel with the drift velocity mu times E. But as the drain voltage keeps increasing, we notice that the voltage difference between the gate and the channel is now different at different locations. At the source, since it's grounded, the voltage difference is always VG minus 0, so whatever the gate voltage is. On the other hand, at the drain, it's VG minus VD, okay? And in the middle of the channel will be something in between, depending on what the channel potential V of X is as a function of X in the channel. Channel length is L, all right? Now, the key point to note is, as the drain voltage increases to VD sat, the channel gets pinched, the inversion region gets pinched off. Now, what will be the value of VD sat? The VD sat has to be VG minus VT, because if that's my drain voltage, the voltage difference between the gate, which is at VG, and the channel becomes VG minus VT, or VT. And we said that VT is the minimum voltage that you need to form the inversion region, okay? So once that happens, the drain current doesn't increase any further, it saturates at what's called ID sat at saturation drain voltage VD sat, okay? And typically under those conditions, the electric field along the channel is so high that the carriers will be pulled out of the inversion region and they'll travel at this saturation drift velocity. And that kind of contributes to the saturation of the current. Now, we said that we're going to set the MOSFET aside for a couple of lectures and just focus on the MOS capacitor structure. And we'll take a cut as a function of depth, momentarily forget about the source drains, and see what happens to the charge in the inversion region in this MOS capacitor structure, okay? And that was the basis of our discussion last time. So here, I'm now looking at the MOS capacitor structure flipped by 90 degrees. So I've turned the previous structure by 90 degrees. Okay, so now my gate is on the left, the gate oxide is over here, and that's my semiconductor. And the reason I'm doing that is I want to correlate that with the band diagrams shown over here for grounded gate. So that's my equilibrium condition, and the negative and positive gate voltages. And we look at the corresponding band diagrams. So in the gate, which can be assumed to be a metal, all right, I mean, these days it's actually a metal, but for a long time it was not really metal. It was a highly doped polycrystalline silicon, which electrically acted like metal. But in this band diagram, I'm showing an actual metal, which doesn't have a band gap. I only have a Fermi level, EFM. And the difference between the Fermi level and the vacuum level is the work function in the metal, Q phi m. Now, in this particular case, instead of the true vacuum level, very often what's done is you reference your potential energies with respect to the conduction band edge of the gate oxide. The oxide, of course, is the insulator. So that's my EC of the insulator. I'm not showing the EV of the insulator. It's a very large band gap. And as I said, in terms of the reference potential energy, it doesn't matter exactly what you choose as long as you're consistent, okay? I mean, you could just as well choose the actual vacuum level also, it doesn't matter. Ultimately, you're looking at differences of potential energy, all right? Now, in the semiconductor, we have EC and EV, and then we said that between the Fermi level in the semiconductor phi s, EFS, to the vacuum level, that's my work function in the semiconductor Q phi s, and then EC to the vacuum level would be your electron affinity, and then if we knew the band gap, you can also pinpoint the location of the valence band, all right? Now, as I said, I've, for starters, assumed an ideal scenario where with zero gate voltage in equilibrium, the bands in the semiconductor do not bend, okay? It just so happens that the Fermi level in the metal and the semiconductor just line up, all right? In general, that will not be the case, as I'll tell you later on in the lecture today, okay? So the reason you end up getting an equilibrium is, remember, you cannot have current flow through this oxide, that's an insulator. You get in equilibrium because you can imagine I'm connecting up the gate to the back surface of the semiconductor substrate. So if the Fermi levels are different, the electrons will flow through this wire connecting the gate to the semiconductor. You assume that there's no leakage current to the gate dielectric itself, all right? Now then, we said that, okay, if you now apply a negative gate voltage, since unlike charges attract each other, and I'm assuming a p-type silicon, it'll attract the mobile holes to the surface, and that's known as an accumulation region. Okay, so I start out with majority carrier holes, and because of the negative gate voltage, I have even more holes at the surface region as reflected by this band bending, all right? On the other hand, if you apply a positive voltage, that'll start pushing the holes away, and now I start forming a depletion region, because if I push the holes away, it'll expose the negatively charged acceptor ions, which contributed the holes, and the acceptors, of course, can move back and forth. Okay, they're locked in the lattice, and that gives rise to a gradually increasing depletion width and an exposed depletion region, all right? In the process, we see that the mid-gap level also, of course, bends, okay? And at some point, the mid-gap level EI will touch the Fermi level at the surface, meaning that the surface has now electrically become an intrinsic semiconductor. If I go beyond that point, the mid-gap level actually goes below the Fermi level, meaning that from the interface up to the crossing point, the Fermi level is in the upper half of the band gap, meaning that it electrically behaves like a N-type semiconductor, even though I had doped it P-type to begin with. And that's known as inversion. Initially, you get what's called strong, weak inversion. But if you keep going, at some point, the band bending will be enough where the EI will bend as far below the Fermi level as it was above the Fermi level, okay? Now that's relevant, that's known as your Fermi potential Q phi f. That's relevant because if you look at the expressions for electrons and holes, we saw in chapter 4, it's given by Ni times e to the power EF minus EI over KT for electrons, or you flip the sign for holes. And EF minus EI is, of course, this quantity phi f, which I'm calling the Fermi potential, okay? In other words, the Fermi potential is a measure of how strongly the material is doped, either P-type or N-type. In this case, of course, it's doped P-type, okay? So then if I have a scenario where the intrinsic level crosses the Fermi level, it's become intrinsic, and then it bends below as much as it was above the Fermi level, that's known as the onset of strong inversion. And the gate voltage that you need to achieve that point is your threshold voltage. Why is that special? You give it a special name because now the surface is as strongly N-type, it's gotten inverted, as it was P-type in the bulk to begin with, okay? So that's why you give it a special name. And we said that at that point, the transistor strongly turns on electrically. And of course, in reality, we'll see, it doesn't really turn on like a switch, digital switch. It'll turn on gradually, but it'll turn on kind of more steeply once you exceed the threshold voltage. If you go beyond the threshold voltage, the approximation is, and it's only an approximation, the band bending doesn't keep increasing. It gets fixed at phi f plus phi f, or 2 phi f. And all that happens is, as the gate voltage becomes more positive and I dump more and more positive charges on the gate electrode, remember this is an MOS capacitor, you'll have to have corresponding negative charges on the other side. Initially, the negative charges were formed by the negatively charged acceptor ions in the depletion region. But once you reach threshold and beyond, you don't expose any more acceptor ions. The depletion region maxes out at what's called W max. And instead what happens is you now start dumping more and more inversion charges in the conduction band, okay? And that, of course, is the charge that are shown in the previous figure, okay? All right, now what we did next was we zoomed in on this third diagram because that's the most interesting case. We're looking at the inversion region and we magnified that. And here I'm only showing the band diagram in the semiconductor, okay? So you have to imagine the large band gap of the oxide over here. And then to the left of the screen, you'd have the Fermi level of the metal gate, okay? So what's shown is this intrinsic level above the Fermi level. That's your Fermi potential. It's a measure of how strongly p-type the material was. And the intrinsic level is bending. So that's my point where the material is intrinsic. And from here to the surface, it's n-type. It's not quite strongly inverted yet. If I bend it by 2 phi f, that's when I reach strong inversion. That's a point shown over here, okay? Now what you can do is you can look at this band diagram and using these exponential dependencies of carrier concentration on band bending, which is given by EI, you have this very horrible looking differential equation that I just sketched out. You'll not be responsible for deriving things like this in the exam, okay? Although it looks horrible, it's actually quite straightforward. It's just a solution of the Poisson equation, which is the divergence of the electric field or the second derivative of the potential, because electric field is minus d phi dx, okay? That's given by the net enclosed charge divided by the dielectric constant of the semiconductor. So you have all the possible positive and the negative charges in general. Here I'm assuming both P and N-type doping. You could have both types, okay? The previous example, we were just talking about the P-type doping. For the P and the N, you put these exponential dependencies that we've been talking about, okay? Times the P naught or the N naught, which is the original value because of doping. So P naught would correspond to NA, N naught would correspond to ND. So if you subtract those, you end up getting this -1 signs. On the left-hand side, you can write the second derivative of potential with position as d dx of d phi dx, which of course is the electric field, okay? Then you integrate both sides. On the left-hand side from 0, where the electric field is 0, which would be somewhere over here in the bulk where there's no band bending and therefore the electric field is 0, to some arbitrary point, d phi dx, and ultimately to the surface electric field. You take that limit, okay? On the right-hand side, similarly, you integrate from 0 to phi, and then ultimately take the limit of phi s, okay? And basically, if you do the integral, it's nice because, you know, exponentials are easy to integrate, constants are easy to integrate, and that's what you end up getting. That'll give you the electric field squared on the left-hand side because it's E dE. Then you have to take the square root, and you get this horrible-looking expression over here, which is what was graphed out here, right? And you can see clearly that initially under flat band conditions, where there's no band bending, of course, the charge has to be 0, space charge neutrality. For negative surface potential, the convention here chosen is the bands are bending upwards. That's my accumulation. I get a carrier concentration which changes as exponentially with surface potential divided by 2 kT, because phi s is a potential right at the surface. You have to average over this whole region, and that introduces a factor of 2. On the other hand, in inversion, which is what's shown in this figure, that's this part. Once again, you get an exponential dependency with a factor of 2 because you have to do the averaging over the entire region. But before the onset of strong inversion with the band bending of 2 phi f, you just have the depletion region where the charge is now going to be the depletion charge, which will scale as a square root of the voltage, okay? And that's that formula that we derived for PN junctions in chapter 5, but I'm simply using that math because it's the Poisson equation here. So W, the depletion rate, in the previous case was a PN junction, but now it's a depletion region over here, is proportional to the square root of the voltage drop across the depletion region in the PN junction. Now it's a voltage drop 2 phi f in the semiconductor. So W is proportional to square root of phi, and then to get the charge, you have to multiply that W times Na times electron charge. So basically the depletion charge scales as a square root of the surface potential, okay? Now, this is an important curve because then from this you can get the capacitance of a semiconductor, which in general we saw is given not by Q over V, but dQ dV. In other words, the slope of these curves. Meaning therefore that in accumulation region or inversion where the slopes are steep, the semiconductor capacitance is high, while in the depletion region, it's a gentler slope and it'll vary as d square root of phi is d phi is, or 1 over square root of phi is. Okay? And that's once again the same kind of formula that we had for the depletion capacitance of a PN junction. Once again, different devices, but same math. Okay? That was then used to look at the CV characteristics of a MOS capacitor. This, like I said, is a very important figure. I want you to study that again and again because I will test you on how to analyze this in the final exam, okay? Now you can kind of get a hand waving picture of this and then use the math also. So what is the hand waving picture? Well, this is two capacitors in series, right? I mean, you have the MOS structure. You have the MO semiconductor structure, right? Where in the semiconductor you have a certain depletion width W, which is voltage dependent, while the oxide itself, in this case, has a fixed thickness D, which I'll sometimes call T-ox also, because in many cases, the oxide happens to be silicon dioxide. So I'll use Ci, the insulator capacitance, or C-ox interchangeably, okay? So in general, Ci is for any insulator of a thickness D, but in many cases, since the insulator happens to be an oxide, I'll call that C-ox divided by epsilon oxide divided by T oxide, all right? That's what generally used in the literature. Okay, so what we find is this MOS capacitor structure is the series combination of two capacitors. The insulator capacitance, which is a fixed voltage independent capacitor, in series with the semiconductor depletion capacitance, CD, which is epsilon semiconductor divided by the depletion width, which is a voltage dependent term, meaning that the semiconductor capacitance is a voltage dependent capacitance, while the CI is not, it's a fixed capacitance, okay? Also remember that the CI is epsilon of the insulator divided by the thickness of the dielectric, while CD is epsilon of the semiconductor divided by the depletion width. Don't mix those two up, okay? I mean, that's a very common error. Now, what do I have if I have a series combination of two capacitors? Well, remember from 411, you have 1 over C overall is equal to CI CD divided by CI plus CD. That's what's shown over here, right? That's a series formula for two capacitors, okay? So CI CD divided by CI plus CD. And let's see how that graphs up, okay? So for negative gate voltages, so this is a plot of capacitance as a function of gate voltage for a p-type silicon. So for negative gate voltages, I'm forming accumulation region. In accumulation, we saw that the semiconductor capacitance is very high. Let's assume it's infinity. So then 1 over C equals 1 over CI plus 1 over infinity. You basically get CI, okay? Another way of looking at it is, you can think of it now like a metal plate, an insulator, and then I have these accumulated holes right at the surface, no depletion region. So it's like two parallel plate capacitors, which would have a capacitance of CI, okay? Just like fixed parallel plate capacitor. On the other hand, as the gate voltage becomes more positive, you start pushing the holes away and you do form this depletion region. Therefore, the capacitance of the semiconductor depletion region keeps decreasing, and the overall capacitance also keeps decreasing, okay? Another way of looking at it is, you have a metal plate over here, the undepleted semiconductor is the other plate, and then the dielectric in between is now a funny kind of a dielectric made up of fixed insulator D in series with a varying dielectric depletion region, W, with two different dielectric constants, okay? And obviously the overall capacitance will keep dropping, okay? It'll drop until I get a maximum depletion width, which I call W max, corresponding to a maximum voltage drop in the semiconductor. What was that? That was given by 2 phi F, right? And beyond that point, the approximation is the depletion region doesn't expand any further and the bands don't bend much further. Okay, now that's only an approximation, as you can see from this figure, of integrated charge as a function of surface potential. So you see that once you reach phi f, I mean, the bands don't bend as much, but they do bend, but not as much. So you can kind of approximate this as a vertical line. And he said that the band bending is fixed at 2 phi f. Like I said, it's an approximation, but it's a pretty good one. Okay. Everybody with me? Okay. So once I reach W max, the capacitance becomes minimum at C minimum, which would be the series combo of C insulator, C semiconductor minimum. Don't confuse the CD minimum, which corresponds to W max, with the overall C minimum. Okay, so when I measure the capacitance voltage behavior, C minimum is what I would measure, and then you have to invert the expression to get the semiconductor minimum capacitance, CD minimum. Okay, and that corresponds to the W max, or a band bending of 2 phi f. Now, what is 2 phi f? Well, if you invert the carrier concentration expressions, that works out to 2 kT over Q log of P over Ni, or Na over Ni, because P is equal to the accepted doping concentration. How did I get that? Well, if you go back a few slides, you get this expression over here, right? So P is equal to Ni, P is equal to Na, equal to Ni e to the power minus Ef minus Ei over Kt, and that, of course, is the Fermi potential. So if you invert that, you take the log of both sides, that's what you end up getting. Okay. I'm repeating all of this because it's so important. Okay. Some of the other things I'll go over quickly, but this is extremely important to understand MOS behavior. Okay. So make sure you do. I will test you on that in the final exam. All right. So once you reach the minimum, if you go a little bit beyond that point, that turns out to be where the threshold voltage is. Now I have strong inversion, and once again, the semiconductor capacitance becomes very, very large, and ultimately you're back to 1 over Ci plus 1 over C semiconductor, which is very large, which is say infinity. So you're back to Ci again. Okay. Now, in terms of the structure, you can kind of think of it also like a metal plate capacitor. You have the metal plate over here, the dielectric, which is fixed. And now you have inversion electrons, which kind of look like your metal plate, okay? So you're back to Ci. Now that is a little bit harder to justify because although I have inversion electrons, you still have the depletion region underneath, right? And you can ask, how come that isn't playing a role? Well, it doesn't play a role because these electric fields get screened out by the strong inversion layer thickness. So that's what physically makes it look like a metal plate. However, there's a catch, okay? It will behave like that only if I vary the gate voltage slowly, okay? Because if I vary the gate voltage slowly, these inversion minority carrier electrons in this MOS capacitor, as I said, which are generated or recombined, will have to be diffused across the depletion region and collect at this inversion region, okay? So if I vary the gate voltage like a sine wave, say, okay? If I increase the gate voltage, decrease it, and so on and so forth, this inversion charge can keep up with that if this gate voltage as a function of time is varied slowly. All right. What am I saying? What I'm saying is, as the gate voltage is slowly increased, more and more inversion charges, which are thermally generated, can diffuse and collect over here. Conversely, as the gate voltage is decreased, those inversion charges are pushed away. Okay. In other words, the inversion charge shown in this figure will go up and down in concert with the gate voltage, okay? And if that happens, that's what I call the low frequency behavior shown in the solid line. You get this capacitance, okay? On the other hand, if I was to vary the gate voltage very, very quickly, if I vary it very, very quickly, these inversion charges don't have enough time to respond to that, okay? Under those conditions, it's as if the inversion region was not even there because capacitance, remember, is given by dq dV, right? So if this charge can respond to that, it's as if it wasn't there. The capacitance bottoms out at the C minimum. Now, the question is, can anyone tell me, what do I mean by varying the gate voltage slowly or fast? Any guesses? Slowly or fast with respect to what? Anybody? You have to unmute yourself if you want to answer.
I imagine you'd want a high frequency setup.
Sorry?
I imagine you'd want it high frequency, you'd want to vary it fast.
No, yeah, no, but that wasn't the question. The question was, I mean, in an actual circuit, yeah, typically you'd vary it at high frequency. No, the question is, what is my definition of high versus low? I mean, high or low with respect to what? That was the question.
Transit time across the depletion region?
Very good. So it's how long it takes for these minority carriers to be generated or recombined and then transit across the depletion region, right? So if the gate voltage varies faster compared to that, the inversion charges can be generated and transit across the depletion region, and you get this curve down below. But if you vary the gate voltage slowly, the inversion charges can keep up and you get this, okay? Now there's one more part to the story. What I just told you is true for an actual MOS capacitor where you don't have these N+ source drains. If the measurement is a MOSFET, where you do have these N+ source drains, you don't have to depend on minority carrier generation in the bulk. These carriers can flow in very, very easily, very, very quickly on a much shorter time scale. That's known as your dielectric relaxation time. So if I did the CV measurements, not for the actual MOS capacitor, but for a MOSFET, both for high and low frequencies, I'd get this curve over here. Okay, it would behave like it was a low frequency CV. Okay, so there's a lot to the story. And as I told you also,
Can you say that again? Why it's different for a MOSFET?
yeah, so for a MOS capacitor where you don't have these source drains, what I'm showing over here, this is the high frequency, that's a low frequency. While for a MOSFET, both high and low frequency would correspond to this solid blue line, okay? Because now, even at high frequency, carriers don't have to depend on generation recombination in the bulk. They can just flow in laterally from the source drain on a much shorter time scale, okay? All right, the other thing that we discussed was extracting parameters of the capacitor from the CV. So either in accumulation or in inversion over here in low frequency, that's CI, which is given by epsilon epsilon insulator divided by the thickness of the insulator. So clearly you can immediately calculate what the thickness of the insulator is if you knew what the dielectric constant was. By the way, these are all assumed to be on a per unit area basis. If I had a capacitor of an area A and I wanted the total capacitance, I simply multiply the CI, which is farads per centimeter square, by whatever the area is, okay? Area is looking at it from the top, obviously, okay? So you have to look at it from the top. You have an area A, okay? Now, from the minimum capacitance, you can invert that and you can calculate the doping using this formula. And I'll show you in the next slide exactly how that's done. It's a little bit complicated because it involves a transcendental equation because you have depletion region, you have doping appear as a log, you also have doping appearing somewhere else. But anyway, let's assume that you can use this formula to get the semiconductor doping based on this expression over here. From that, you can get what's called the debye screening length that we talked about last time, which depends on doping. And that's important because, take my word for it, from the debye screening length, you get what's called the debye capacitance, which enters into the expression for the flat band capacitance as the series combination of the oxide capacitance and the debye capacitance. So knowing what the doping, calculating what debye capacitance is, you can calculate the flat band capacitance, and you can then read off the corresponding flat band voltage, which is the voltage that you need to apply to the gate to achieve this flat band condition. Now, so far, we have assumed that voltage to be 0 in an ideal structure. It's not 0 in practice, as we'll see in just a second. All right. Okay, let's see. Yeah, I think that's pretty much it. Well, then the shape of the curve, as I told you last time, tells you whether it's P or N type, because it will go down slowly in depletion and go up steeply in inversion. So this is a P type. On the other hand, if it was an N type substrate, it will go down steeply and then go up slowly. Okay, so there's a lot of information you can get out of this. Next, what I want to do, and this is also very, very important, is come up with an expression for this threshold voltage that I've been talking about, okay? So once again, as I said, that means band bending of phi f plus phi f or 2 phi f, okay? So what I want to calculate is what gate voltage do I need to achieve that, okay? Well, over here, I'm showing the band diagram and the corresponding charges that are developed on the two electrodes. So on the metal plate, I have metal charges per unit area, coulombs per centimeter square of QM. There's no charges in the oxide, but there is electric field, okay? And then the charges in the semiconductor, which have two components, okay? So one is this depletion charge due to the acceptor ions that are exposed over a certain depletion with W, which ultimately will reach W max, okay, which are called WM over here at threshold. But then once I exceed that, you start also having a lot of inversion charges, QN, which is, of course, almost like a delta function charge. These inversion electrons are mobile. They'll pile up as close as they can to this interface. The acceptor ions, of course, are locked in the lattice. They can't move around, okay? So what I have to do is find what gate voltage I need, VT, to achieve this condition, right? Well, the gate voltage that I apply has to be dropped partly across the oxide and then partly across the semiconductor, right? Because over here, you can assume that substrate is grounded, say, right? So the voltage dropped across the oxide, I'm assuming a positive gate voltage. That's why this formula level here is going down, while the formula level in the semiconductor is over here. Notice, therefore, this is a non-equilibrium scenario, okay? But although it's non-equilibrium, there's no current flowing because the insulator, remember, is a dielectric, right? So you have to imagine that I'm connecting it to the battery like so, okay? The metal electrode to a battery V to the back side of the semiconductor, but there cannot be any current flow because I have an insulator in the middle, okay? That's why it's like a capacitor. In a capacitor, of course, you have equal and opposite charges on the two electrodes. So if I apply a positive voltage here, I get a charge of plus Q, equal charge of minus Q on the other side of the electrode, where this minus Q is made up of two parts, the negative exposed acceptor ions and the negative mobile inversion electrons, okay? So how is the voltage drop? Like I said, once again, it's dropped partly across the oxide and partly across the semiconductor. Now the voltage drop across the semiconductor is easy. I've already calculated that as 2 phi f or 2 kT over Q log of Na over Ni, okay? This is the voltage drop across the oxide, okay? How do I figure that out? Well, that can be done because as far as the oxide or the insulator capacitance is, that is a fixed voltage independent capacitor, right? That's given by epsilon I divided by D, or equivalently epsilon oxide over T ox, in which case I'll call that C ox, okay? So people go back and forth between those two terminologies. This is a fixed voltage independent capacitor, right? And that capacitance therefore can be written as Q over V. You don't have to do that dQ over dV business, right? Because it's a fixed capacitance. So somehow, if I can figure out the charge and I know what the capacitance is, I can then figure out the voltage drop across the insulator, which is this voltage, right? So I already know CI. If I can somehow figure out the charge, I can get the voltage drop, right? Because voltage drop would be the charge divided by CI, okay? Now what is the charge? Well, it's either the charge on the metal electrode or the charge on the semiconductor. They have to be equal and opposite to each other, okay? Now I can't easily calculate the metal electrode charge, but I know how to calculate the semiconductor charge, right? Right at the onset of threshold, I haven't started pumping a lot of inversion charges. It's mostly the depletion charge, right? Now what is that? Depletion charge is Q Na times W, right? Depletion rate. That's my depletion charge. And at W max corresponding to VT, the W would be, sorry, WM or W max, okay? That's what's shown over here. Now, how do I get the WM? Well, you use the same formula that I've been talking about all the time, okay? Which is this voltage drop across any depletion region that we derived for p-n junctions is equal to half electron charge Na W square over epsilon of the semiconductor, right? Here, the voltage drop would be 2 phi f. That's maximum band bending. So clearly I can use this to come up with W max by taking the square root, and then get the corresponding depletion charge as Q Na times W max. That's what I do over here. Okay, once I get the maximum depletion rate in terms of the band bending in the semiconductor, which is 2 kT log of Na over Ni, and then a whole bunch of other parameters, and get the depletion charge per unit area like this. Now notice it as the right units. Na has units of number per centimeter cubed. W has units of centimeter, so that's number per centimeter square, and then with the charge, multiplied by the charge of the electron. So that's coulombs per centimeter square. Okay, everything is figured out on a per unit area capacitor basis. Okay, once again, if you wanted the total charge in a real capacitor, you then multiply by the area of the capacitor. Okay, everybody with me? All right, so now that I've gotten the charge on this plate, the voltage drop would be that charge divided by the capacitance of the dielectric. So that's the voltage drop across the oxide. That's the voltage drop across the semiconductor. That therefore would be the applied gate voltage, the threshold voltage. Now, as I was saying in the previous figure, solving this is a little bit complicated because unfortunately the doping appears in two places. You have the log of the doping here, and you have doping in the denominator. So to solve this, you really can only solve it on a computer or using numerical tricks that were done to come up with this expression over here. Okay, so you need to use this to solve one of the homework problems. Okay, so the corresponding electric fields are shown over here as a function of position across the oxide, assuming there are no charges in the oxide, which is also not true in general. The electric field across oxide is constant, the slope is constant. There's a sudden jump downwards in the electric field, and then in the depletion region over here, the electric field changes linearly with position, exactly as in the case of p-n junction with constant doping on either side. Same math, although the structure is different. Okay, I'm solving the Poisson equation. Once I get the electric field profile, how do I get the potential? Well, potential is minus dV dx, sorry, is equal to electric field, and therefore V is equal to integral of minus E dx. So I simply have to integrate this. If I integrate a constant, I get a potential variation that's linear with position. If I integrate a linear variation, I get a parabolic dependency, right? And this would then reflect in the band bending. So this is a parabolic shape reflecting the mirror image of this parabolic variation of the potential. Okay. One question: why do you think the electric field drops abruptly at this interface between the oxide and the semiconductor?
Different dielectric constant.
Very good. So from EMAG, remember what's constant across this interface is what's called the electric displacement. So epsilon insulator times electric field in the insulator must be equal to epsilon semiconductor times electric field in the semiconductor. So the ratio of the two electric fields would be the inverse ratio of the dielectric constant of the oxide and the semiconductor. Okay. All right. So far we have been assuming an ideal structure, ideal in the sense that it just so happens that the gate voltage was 0, where I had equilibrium conditions. The Fermi level in the semiconductor just happened to line up with the same energy as the Fermi level in the metal, so that when I join the two with a wire, there will be no charge flowing across, keeping the bands flat in the semiconductor, as shown in the band diagram over here. Okay, but in general, that's not the case. In general, the work function in the metal and the semiconductor, phi m and phi s, would be different, so that if I join them with a wire at the back, charges would flow, not through the dielectric, because the dielectric cannot conduct, but they would flow through the wire connecting the metal electrode to the semiconductor. Okay, which way would they flow? Well, our old rule is electrons flow from the high Fermi level region to the low Fermi level region. until in equilibrium the Fermi level is constant everywhere, and holes flow the other way. Now, in this case, since it's a p-type semiconductor, it makes sense to think in terms of majority carrier hole flow that will flow from low to high, right? But of course, here, Fermi levels are the same, so there's no carrier flow. Therefore, there's no band bending, and the bands are flat band voltage of 0. As I said, however, that's not going to be the true case in general. There are two sources of band bending or non-zero flat band voltage. Okay, so here I'm seeing why the so-called flat band voltage in general is not 0. Okay, the first is because of differences of the work function of the metal and the semiconductor. Okay, so here I'm assuming that the work function of the metal from here to the vacuum level is larger than the work function of the semiconductor. Okay, so if that's my phi m, and that's my phi s. Phi s is greater than phi m. Okay, so here, if I join the two together, the wire at the back, which way would the holes flow? Well, they'll flow from the low Fermi level region into the high Fermi level region, right? And if that happens, I end up getting a depletion region, right? So in equilibrium, if I've joined them with a wire and there's no voltage source, in equilibrium, the Fermi levels have to line up. And the only way they can line up is the holes, the majority carriers flow from the solid into the metal electrode, or the electrons flow the other way. In the process, they form a depletion region, and therefore there's band bending. So notice that in equilibrium, the bands are not flat in the semiconductor. That is not the flat band condition. Okay? So how do I achieve flat band? Well, you have to apply a sufficient voltage corresponding to the difference of the work functions, okay, to kind of counteract that and push those holes back as shown in this figure over here, okay? So the first contribution to the flat band voltage is called phi ms, and that's nothing but phi m minus phi s, okay? So if you apply that voltage, you'd undo this band bending, okay? Now this is shown over here for practical silicon MOSFETs. As I said, for a long time, the gate metal was not a true metal. It was highly doped N plus polysilicon, or generally N plus polysilicon. Now this shows this phi ms as a function of substrate doping for N-type silicon and P-type silicon. Okay, now let's see if we can understand that. Well, if I have my semiconductor over here in the channel, that's EC, EV, and then I have the oxide, and then I have the gate, which is also actually a doped polysilicon, which will have band gap, EC-EV, but I'm saying that it's N plus. If it's N plus, where is the Fermi level in the metal, in the polysilicon gate, which looks like a metal gate, B? Well, it would have to be close to the conduction band edge, right? So that's my EFM. So if I measure it from the vacuum level, that's my phi m, right? So it's, can anyone tell me what is the phi m equal to in this case, approximately? If my Fermi level matches the conduction band edge, phi m is basically equal to, what is the difference from the conduction band to the vacuum level called?
Electron affinity.
Excellent. So that's basically the electron affinity of polysilicon or silicon, okay? Polysilicon is silicon, except that it's not single crystal, okay? On the other hand, here I'm plotting it as a function of doping in the semiconductor channel, right? So if it's N-type, the Fermi level is in the upper half of the gap, and I'm showing this as a function of increasing N-type doping. Well, how the Fermi level vary in the semiconductor as it becomes more and more N-type? It moves closer to which band edge? Conduction band edge, right? So so asymptotically, what would be phi m minus phi s for very high N-type doping?
0.
Excellent. That's why it asymptotes to 0. On the other hand, for P-type, the Fermi level would asymptote to the valence band, right? So what would be phi m minus phi s in the high doping limit? You would have to correspond to
Band gap.
Band gap. You guys are very good. Okay, so that's about 1.1 EV. Okay, so try to get a visual idea of how these values depend on the band diagram. Because in exams, I'll give you a different problem, right? So unless you really understand the physics, you'll not be able to get it. All right, so that was the first contribution to the flat band voltage. The second contribution is due to charges that are typically seen within the oxide. Now, so far we've been pretending that this oxide insulator is perfect, okay? That's not true in general. A real practical oxide will have different types of charges in them, which are roughly grouped into 4 categories as shown over here. Here shown for silicon dioxide. In modern day MOSFETs, of course, we'll see in a second, it's generally not silicon dioxide, but what are called high dielectric constant dielectrics, also known as high K dielectrics, okay? I'll talk about that in a second. Things like hafnium oxide. So here I'm showing a blown up view of this structure. So that's my metal electrode shown in dark. My semiconductor is shown in this lightly shaded region, and the oxide is shown in this clear region. And I'm showing the origin of the different types of charges that you have, okay? So the first type of charge that you have is called the interface trap charge, QIT. And the origin of that is right at the interface, we have a transition from single crystal silicon with this nice diamond type structure into SiO2, where SiO2 in general is an amorphous structure with a different lattice constant, okay? In fact, because it's amorphous, it doesn't have a well-defined lattice structure, okay? So in that case, would you expect that there would be a lot of broken dangling bonds or not at this interface? Well, clearly you would, right? Because you're going for a nice, well-ordered crystal structure into something that's highly disordered, right? So as a result, you get a lot of broken bonds, distorted bonds, and that ends up creating a lot of energy levels within the band gap of the semiconductor, okay? That's this interface trap charge, okay? Slightly above that, slightly farther away, you have what are called the fixed charges, okay? Now, these are also due to structural defects in the oxide or this high K dielectric, okay? Now, the reason you differentiate between the two is we'll see in a second that these fixed charges, as the name implies, cannot change their charge state. If they're positive, they stay positive. If they're negative, they stay negative. On the other hand, these interface charges, because they're right at the interface, they can exchange charges with the semiconductor, conduction band and the valence band, relatively quick. So therefore, they're sometimes also known as fast interface states, while these are fixed. These can change their charge occupancy with semiconductor band bending, while these cannot. Why do they change charge occupancy with band bending? Well, remember, if you look at the Fermi-Dirac distribution function, if you plot f of E as a function of E, the Fermi level is somewhere over here. Energy levels below the Fermi level are occupied, while those above the Fermi level are not occupied, right? So here, which of these interface states would be occupied? Well, these states which are below the Fermi level would have electrons trapped in them, while the ones above that would be empty. Now let's see what would happen as a function of semiconductor band bending. If I bend the bands, some of these states which were initially above the Fermi level and were unoccupied would move below the Fermi level and would trap electrons. But the same states, if the bands are bent the other way, would give up electrons, okay? Now you can describe the same language in terms of electrons or holes. And since I'm dealing in this case with a p-type semiconductor, it's more reasonable to talk in terms of holes, okay? So in this case, these are unoccupied by holes, while these are occupied by holes, and vice versa. But the important point is the occupancy by holes can change relatively quickly as the gate voltage over here is changed relatively quickly, okay? And the bands bend up and down. On the other hand, the fixed charges cannot do that. The third category is called oxide trap charge. These are much farther away toward the bulk of the dielectric, okay? And there can be various sources for that. So we'll see one source would be when you actually operate a MOSFET and you flow carriers from the source to the drain. So my source would be over here, drain over there. Some of these electrons can gain a lot of kinetic energy from the applied BD, and they can be injected into the oxide and trapped there as what are called hot electrons, okay? We'll discuss that in great detail next week when we start talking about MOSFETs, but just keep that at the back of your mind. This happens to be a major source of failure for an IC, okay? The reason ICs don't last forever, they're typically designed to last for maybe 10 years or so, is because of this hot electron generation or hot hole generation, which can be trapped in the oxide, and over time, you change the electrical properties, you change the flat band voltage, therefore the threshold voltage, and therefore at some point the circuit fades, okay? And the typical design time window is about 10 years. But it turns out, these days we get rid of our iPhones or laptops way before 10 years. In most cases, it's not a practical limitation, okay? The fourth category, and in some senses is even more problematic, are called mobile ionic charges. And these are due to alkali ions, such as sodium or lithium, which are elements in the periodic column 1 of the periodic table, okay? Why are they problematic? As the name implies, these can move back and forth. They're mobile. So if I apply a positive gate voltage, remember like charges repel each other, they'll push these sodium ions to this interface. They'll be close to the semiconductor. Now, if this was a p-type silicon, once again, like charges repel each other, these positive sodium ions would repel the holes. They would cause more band bending, okay? On the other hand, if I apply a negative gate voltage, the sodium ions will slowly drift back. This doesn't happen very, very quickly. It drifts back and forth maybe on the time scale of minutes or hours. But as a result, if the ions move close to this electrode, they induce charges in the gate metal. They don't do anything to the semiconductor. On the other hand, if the ions move to this electrode, they repel the holes over here, okay? Now, what impact does it have on the band bending? Well, if you have these charges, say, assume they're positive charges, as I said, they would repel the holes, which are the majority carriers in this p-type silicon shown over here, right? And it would cause band bending. To undo that band bending, we'd have to apply negative voltage. So now my Fermi level in the gate moves up in energy. So I then attract back those holes back to the surface, and I reach this flat band condition shown over here. Okay, so the negative gate voltage in this case counteracts the repulsive forces of these positive charges shown. And that's the second contribution to the flat band voltage. To get that contribution, however, to the flat band voltage, you have to sum up or integrate all these charges, right? The charge density, rho, as a function of x prime. X prime is measured from in this direction, okay? From this interface. So that's 0 up to d, d being the thickness of the dielectric. Okay. What you have to do is you have to do an integral of the charge, but you have to do a weighted sum, meaning that you don't count all charges equally. Why is that? Well, if I had a positive charge over here, which is that x prime of 0, that causes an image charge on the metal electrode, right? It doesn't have any impact on the semiconductor band bending. Therefore, I weight that charge relatively less. X prime over d is small. On the other hand, if the charge gets closer and closer to this interface, x prime approaches d, I count those charges very heavily. So it's a weighted sum of these charges. You guys with me? So you don't just sum up all the charges. Charges that are closest to this interface, you count more. Charges that are close to the metal electrode, you count less. Because you want to figure out the impact of those charges on the semiconductor band bending, okay? So that's the second contribution to the flat band voltage. This integral is lumped as a delta function charge Qi. So you kind of map all these distributed charges to delta function Qi. So this is the weighted sum of all these charges, has units of coulombs per centimeter square, kind of mapped at this interface, okay? So that's Qi divided by the semiconductor, the oxide dielectric capacitance, Ci, okay? So that gives you the second contribution. So now you're able to put all these terms together to get the actual expression for the threshold voltage. So earlier when you had the ideal diode, we assumed that the flat band voltage, which is these first two terms, was 0. So to get that, you added the voltage drop in the semiconductor, to the voltage drop across the oxide, where QD equals Q NA W max, where W max depended on doping in two places, log of doping over Ni in the numerator, and then log of Na over Ni in the numerator, and then Na in the denominator. But now we've added two more terms, which is the work function difference between the metal and the semiconductor, and then the effect of the charges mapped to a delta function charge at the interface over Ci. Okay. Now the variation of this threshold voltage with doping for N channel and P channel is shown over here. So what we've been talking about so far are so-called N channel devices, where you have N plus source drains, and you typically have a P-type silicon, okay, so that you have to form an inversion layer. Okay. On the other hand, you could have the P channel, where you have P plus source drains, and now you have an N-type silicon to begin with, but then you induce holes. Okay, so this terminology refers to what type of channel you have. Okay, so here holes are the majority carrier, where here electrons are the majority carrier. Okay. Any questions? All right, so far we've been talking, well, we started with the MOSFET, and we said that let's set aside the source drains for a second, and let's just focus on the MOS capacitor structure. That's what we've been doing for the last lecture until now, okay? And we'll keep doing that. But now, momentarily, let's see what the impact of this source drain would be if it was a MOSFET, okay? It has an impact on the threshold voltage as shown in this figure, okay? And this effect is known as the substrate bias effect. What am I talking about? Well, if I had a MOSFET structure, you reference all your voltages to the source, which is assumed to be grounded. So Vs is always assumed to be ground. And you reference your gate voltage and drain voltage with respect to the grounded source. Now, so far, we've been pretending that the substrate is grounded, but in general, the substrate can also have a bias applied to it, which could be different from the source voltage. And if that's the case, really, if you think of a MOSFET, it is not a three-terminal device. It's actually a four-terminal device. You have the gate, source, drain, and the substrate is your fourth terminal, okay? And in actual circuit applications, you can make use of that very cleverly, get all kinds of very interesting behavior. So in this particular figure, I'm seeing what the effect of this substrate bias is on the threshold voltage. Now, why would that have an effect? Well, to understand that, you have to look at the band diagram across this, okay? We showed that before, a couple of lectures back, okay? So we said that, well, let me draw it over here to correspond with this. So let's start off in equilibrium. My Fermi level is over here. The N plus source, the conduction band's closest compared to the valence band, okay? Same over here. But in the P-type channel, the valence band is closer than the conduction band, and you get this barrier, remember? Sorry. And when you now apply a positive gate voltage, you push these bands down, and that's how you get the inversion region once you exceed the threshold voltage. Okay? Now, all of that was assuming we didn't have to worry about the source drains. But now you have a source drain. You assume that this potential is grounded, okay? And now let's see if I change the substrate bias, instead of making that grounded also, suppose I make that negative. Now here, across the source and the substrate, that's an N plus P junction. That is this potential barrier, right? N plus P junction potential barrier. If I apply a negative gate voltage to the substrate, am I forward or reverse biasing this N plus P junction? I'm reverse biasing it, right? And what happens to the band bending and the potential barrier in a reverse bias PN junction? Does it increase or decrease? Well, it increases, right? So it'll now go up like so, right? Where now this barrier would be the initial built-in junction potential V0 plus this additional VB, if it's a reverse bias. Now, if I've increased the barrier by increasing this potential barrier by reverse biasing this junction, would the gate have an easier or harder time to reach this inversion condition? Obviously, it'll be harder, right? Because now the gate has pushed down this band diagram from a much higher potential barrier, right? To reach a low enough barrier so that these carriers can flow in from the source drain and form this inversion region. So once you understand that, you can see that the threshold voltage would increase with increasing substrate bias, assuming it's a reverse bias substrate. And generally, that's what's done in a circuit, because you can't afford to forward bias it, because then you'd have a lot of leakage current flowing into the substrate. Okay. So basically, if you go through the math, okay, you find that it increases as a square root of 2 phi f. That was the initial potential barrier, 2 phi f, okay, minus VB. VB is negative, so minus VB is actually a positive quantity, and the threshold voltage increases with reverse bias of the substrate, and this particular effect is known as a body effect or the substrate bias effect. Okay. Now later on, when we talk about MOSFETs next week, we'll see how you can make use of this in circuits. So a MOSFET is a
It seems like sometimes we talk about N-channel being P-type substrate with an N-channel formed, and sometimes it means an N-type substrate. Is that just me confused, or does sometimes we refer to it differently?
So the channel type refers to what is the carrier type that's flowing from the source to the drain. Okay. So if it's electrons that are flowing, those are called N-channel. If it's holes that are flowing, that's P-channel. Okay. And that would be whatever the doping type of the source and the drain is. All right. Now you're sort of on the right track. So suppose it's N-channel as shown over here. Here I'm assuming I have a P-type substrate, so that I have to induce electrons, okay, in this N-channel. But it could have started with an N-type silicon, N plus source drain. That would still be an N-channel, but now it would be a channel that's preformed by the doping, okay? Such devices, such MOSFETs are known as depletion mode MOSFETs, okay? And essentially, the threshold voltage for such a device would be negative. So if I was to plot ID as a function of VG, it would do this, rather than in a regular P-channel, P substrate device, it would do this, okay? So these devices are known as enhancement mode devices, while if the substrate was doped N-type, those are called depletion mode devices, okay? I'll discuss this next week, so let me not waste time on this now, okay? Generally speaking, these types of devices are undesirable, because that means that the transistor is normally on. It's conducting current, even if the gate voltage was 0. So in most circuits, you want a normally off device or an enhancement mode device, which means that you make the N-channel MOSFET in a P-type substrate, okay? And like I said, I'll go over this in great detail next week. In the interest of time, I'm not going to go over the homework problems or the solved problems. You look at those. Okay. To wrap up our discussion about MOSFETs, I want to point out one important application in an integrated circuit, which is the formation of what are called field regions or isolation regions. Okay. What is the issue? The issue is, when you make an IC, of course, you're not going to just have a discrete MOSFET connected with a wire with another discrete MOSFET. I mean, the essence of an integrated circuit is you integrate all these MOSFETs, literally billions of them, on a piece of silicon, maybe a centimeter by a centimeter, okay? I'm over here showing one MOSFET. There could be another MOSFET on this side, another MOSFET to the left, and no, MOSFET front, back, and all over. And they're all crammed in as tightly as possible to save real estate. And they're all made on a piece of semiconductor silicon, right? Now, because it's a semiconductor, unless I'm careful, you could have leakage paths between this MOSFET and neighboring MOSFETs, right? Because I'm making it on a semiconductor. Now, it's not a metal, so it's not a short circuit, but it's not an insulator either, right? So you could have current flow between neighboring transistors, which would then make your circuits not work properly, because you only want the two devices to interact if it was purposely connected by a wire, as shown over here, for instance, right? Now, the question is, how do you guarantee that the two transistors would not leak unless I want to have current flow by, by actually connecting this, say, drain to this transistor or whatever, okay? Because, what could happen is I could have a metal wire from another circuit element go across the structure, okay? And I don't really intend this metal wire to connect this transistor to this transistor. How do you ensure electrical isolation, okay? The way you do that is you form a region with a very, very thick oxide, which is called a field oxide. And that will guarantee a very high threshold voltage of an unintended parasitic transistor that's formed over here. Why is it acting like a transistor? Well, I have an N+ region over here of this MOSFET, another N+ region of the neighboring MOSFET. I have an insulator, kind of like a gate dielectric, and I have a piece of metal because of a wire, interconnect wire maybe, right? Well, the silicon is stupid, right? I mean, it doesn't know that this wasn't meant to be a MOSFET, right? I mean, it looks at the structure, it sees N+ dope region here, an N+ dope region here, a dielectric with a metal gate on top, right? So it has all the elements of a MOSFET. And unless I'm careful, you could have some electrical conduction this way, right? That's unintended. So to guarantee that there's no unintended current, if I could somehow design the threshold voltage of this unintended parasitic MOSFET to be very, very high, then although in principle you could have current conduction, in practice you'd never conduct, right? Now, what does very high mean? Well, if I make the threshold voltage much, much greater than the power supply voltage VDD, suppose I have a 5-volt IC, right? And the threshold voltage is designed to be 20 volts over here. This part will never conduct. What is the threshold voltage over here? These will be typically designed to be plus 0.7 volts or minus 0.7 volts in NMOS and PMOS. Okay, I'll tell you why next week. But here, you may have a threshold voltage of, say, 20 volts. How do you guarantee that? Well, let's look at the threshold voltage expression. So if you look at the VT expression, it has 4 terms. And the key point is the CI term over here. What is CI? That's epsilon of the insulator by the thickness of the insulator. Or equivalently, we can write it as epsilon oxide over T oxide, if it's silicon dioxide or some other oxide, okay? Now, it turns out, in this case, for N MOSFETs, okay, the depletion charge is negative because it's minus QNA, except there's a negative W. Okay, so if it's an N-channel device made in a P substrate, this QD is negative. So that negative and this negative makes it a positive term. On the other hand, for P MOSFETs, it's negative. But let's just, for our discussion, let's think of an N-channel MOSFET that we've been talking about, okay? So this term is positive because it's minus times QD, but the QD itself is negative, okay? And then this is the interface trap charge because of charges in the dielectric divided by CI. The trap charges typically tend to be positive, so this gives you a negative term, okay? The most important part relevant for this discussion is this term over here, okay? So the question for you is, I want to make my VT very, very large, right? Say 20 volts, for example, or much higher than the threshold, the power supply voltage. What do you think I could do to make that happen?
Thick oxide?
Very good. You want CI to be as small as possible because it's minus times minus, which is positive. If I make the denominator very, very small, the VT would be high. How do I make the denominator very small? I make the oxide very, very thick, right? Because if this becomes large, that becomes very, very small, okay? The other thing that you could do, of course, is also change the doping term in the isolation region. And both of those are done, okay? So you make the oxide much, much thicker than the gate oxide in the MOSFET. And sometimes you can add some additional doping that's sometimes called a channel stop doping, because I'm preventing the formation of a parasitic channel. Okay. Now, other things that we'll discuss next week are in an IC, you can also tweak the threshold voltage by doing what's called an ion implantation in the channel region, which will form a charge distribution in the channel. That will impact the QD term in the previous formula, and you can fine-tune threshold voltages. Okay, in the last few minutes, I want to quickly go over a couple of other CV behaviors, okay? I've already kind of touched upon this. So we are looking at the charges in the dielectric, and we said that there are 4 types over here. And one of them we said was right at the interface, QIT, which is also sometimes called a fast interface charge. And then we also talk about these mobile charges. Those are the 2 that I'll be addressing now, okay? So the fast interface charge is given that name because as I change my gate voltage and the bands bend up and down, these charges at the interface go above or below the Fermi level, and then they can exchange charges with the semiconductor relatively fast. Not super fast, but relatively fast as I vary the gate voltage. So if I vary it like this, these interface charges can respond to that. On the other hand, if we vary the gate voltage very, very quickly, even these fast interface charges can't respond to that, and they'll not show up. Now, anytime I have charge storage in somewhere, what kind of a circuit element do you think that gives rise to? Anything that can store charge is tantamount to capacitance, right? Therefore, these defects, which can trap charges, are going to be effectively a capacitor in the circuit. So this equivalent circuit would be the CD or the CI, misspoke, CI or COX in series with the depletion capacitance of the semiconductor. But now, in parallel with that, we have what's called the interface capacitance because these charge storage elements. And if I have 2 capacitors in parallel, they'll add up, and the whole thing is then in series with CI. That will have an impact on the CD behavior as shown over here, okay? That's what's shown in this equivalent circuit. So you have the depletion, semiconductor depletion capacitance, now in parallel with the fast interface state capacitance, in series with the CI. And therefore now, compared to the scenario where there were no interface charges, interface capacitance, if I have interface trap charges, the overall capacitance measured here would be larger because these 2 add up in series. But that will add up and respond only if I do the measurements at low frequencies applied to the gate voltage. If I vary the gate voltage relatively slow so that these interface charges can respond to that. On the other hand, if I vary it at a high frequency, even these fast interface trap charges can't keep up with that. Therefore, for all practical purposes, you can kind of ignore this. Why is that relevant? Well, by comparing the difference between low and high frequency CV measurements, you can hopefully then get some information about the distribution of these fast interface type defects. And that's exactly what's done. And that's a very important measurement because these have a very important impact on the MOSFET characteristics that we'll discuss next week, okay? It'll impact what's called the subthreshold behavior. The other thing that the CV measurements can tell you are the impact of these mobile charges that we talked about, with the sodium ions, which slowly can drift back and forth. Well, as I told you already, if these ions move close to the semiconductor, and if it's a P-type silicon, they'll push away the holes, it'll have maximum impact, right? On the other hand, if these mobile charges drift to this electrode by applying a negative gate voltage, they'll cause an image charge on the metal plate. It will not cause any band bending in the semiconductor, right? So that's why you have to do this weighted sum in terms of figuring out the impact of these charges on the flat band voltage. Remember that? So the point is, for the mobile charges, this rho of x is not constant. As they move back and forth, this rho of x varies. Therefore, the flat band voltage would vary, which is a huge reliability problem. Okay? And that is measured by the so-called bias temperature stress measurement. So you make a MOS structure, you first apply a positive gate voltage, you measure the CV, and we see how we know how to calculate the flat band voltage from that. But then you heat it up to allow these ions to drift more easily, apply a negative voltage, measure that. And the difference between the two, delta flat band, will be the mobile charge divided by Ci. Okay, so you can measure the mobile charges, and the source of which are sodium ions. What are sources of sodium? Well, in IC processing, if you look at the Silicon Run video, you'll see that photoresist is developed using sodium hydroxide developer. In fact, in the 440 lab, you do that, okay? Or if I'm an engineer working at Intel, if I accidentally touch one of the wafers with my bare hand without wearing gloves, because we eat salt, which is sodium chloride, the human hand would be a nice, rich source of sodium. So you contaminate your shapes. If you did that working at Intel, the rule is they'll immediately take you out into the parking lot and shoot you on the spot. Okay, and that's the end of your career. Anyway, on that happy note, let's wrap up. They won't shoot you, so don't get scared. Intel is a great place to work. So in the next class, we'll quickly say a few words about current voltage characteristics of MOSFETs, and we'll see that these oxide dielectrics, because they are so thin, although ideally they're an insulator, they're now going to be subject to tunneling leakage currents that we have seen already in the context of PN junctions, okay? And that is a huge scaling problem for silicon dioxide, which is what led to the advent of what are called high K dielectrics, high dielectric constant dielectrics. We'll start off with that and then start talking about MOSFETs. Any questions? All right. See you next week.